Narration. Photoelectric effect. Composite wave. Total words approximately 230. Estimated duration approximately 92 seconds at 2.5 words per second. Paragraph timestamps. Estimated. Replace with whisper output once TTS runs. Para 1. Hook. Over 10 seconds. 25 words. Para 2. Approach. 10 to 31 seconds. 52 words. Para 3. Step 1. 31 to 49 seconds. 45 words. Para 4. Step 2. 49 to 62 seconds. 32 words. Narration. 5. Step 3. 62 to 80 seconds. 45 words. Para 6. Step 4. 80 to 92 seconds. 31 words. Answer card hold. 92 to 97 seconds. 2 light waves strike a metal surface, each with a different frequency. Which one determines the maximum kinetic energy of ejected electrons? And what is the classic trap hiding inside this wave equation? Here's our approach. First, we extract the 2 angular frequencies from the wave equation. Then we identify which one matters. Only the highest frequency photon governs maximum kinetic energy. The key move is using h-bar, not h, since the equation uses angular frequency omega. Finally, we subtract the work function to find our answer. The wave equation has 2 angular frequencies. Omega 1 equals 3 times 10 to the 15, and omega 2 equals 12 times 10 to the 15 radians per second. These are angular frequencies, omega, not regular frequencies nu. Notice the amplitude of 60 is completely irrelevant here, because it controls how many photons arrive, not the energy of each photon. In the photoelectric effect, only the most energetic photon determines maximum kinetic energy. So we take omega max equals 12 times 10 to the 15 and ignore the smaller frequency entirely. 1 photon hits 1 electron, and the highest energy photon wins. Now, photon energy equals h-bar times omega, where h-bar is h divided by 2 pi, about 1.05 times 10 to the negative 34. Multiplying by omega max gives 12.6 times 10 to the negative 19 joules. Converting to electron volts, that is 7.875 electron volts of photon energy available to each electron. Subtracting the work function of 2.8 electron volts, the minimum energy needed to escape the metal, leaves maximum kinetic energy of approximately 5.1 electron volts. Option 3 is correct. Here's a classic thermodynamics problem, a gas geyser that heats water. We're told how fast the water flows and how hot it gets. The question is, how much gas does it burn every second? Here's our approach. First, we convert the water's flow rate from liters per minute into a mass per second. Then, we calculate how many joules of heat the water needs every second to rise by 60 degrees. Finally, we apply energy conservation. The heat released by the gas must equal the heat absorbed by the water, and solve for the gas burn rate. Step 1. 5 liters of water flow every minute. Water has a density of 1 kilogram per liter, so that's 5 kilograms per minute, which is 5 kilograms per 60 seconds, or about 0.083 kilograms per second, or 5 over 60 kilograms per second. Step 2. The water temperature climbs from 27 to 87 degrees, a rise of 60 degrees. Multiplying the mass rate, specific heat, and temperature rise gives us 21,000 joules per second. That's the power the geyser must deliver. Every gram of gas releases 50,000 joules when it burns. To deliver 21,000 joules per second, we divide 21,000 by 50,000, giving us 0.42 grams per second. The answer is option 4, 0.42 grams per second. Energy in equals energy out, a direct application of conservation of energy. 2 springs, 2 measurements, 1 small calculation that trips up most JEE students. What's the percentage error in the equivalent spring constant when springs are connected in parallel? Here's our approach. First, we'll find the equivalent spring constant using the parallel combination formula. Then, we'll apply the golden rule of error propagation for addition. Finally, we divide to get the percentage error. 3 clean steps. Step 1. The parallel spring formula. When springs are in parallel, they both stretch by the same amount, and their restoring forces add together. So the equivalent spring constant is simply their sum. 10 plus 20 gives us 30 newtons per meter. Step 2. Error propagation. Here's the key rule. Whenever you add two quantities, their absolute errors always add 2. So the error in K equivalent equals 0.2 plus 0.3, which is 0.5 newtons per meter. Step 3. The percentage error. Divide the absolute error by the value and multiply by 100. That's 0.5 over 30 times 100, giving us 5/3%, exactly 1.67%. The answer is option 3. And the insight to remember, for addition and subtraction, always add the absolute errors, never the relative ones. This circuit has 4 logic gates, and we need to figure out what single gate the entire circuit behaves as. Let's trace through it step by step. Here's our approach. First, we'll identify each gate type from its symbol. Then we'll trace the Boolean expression gate by gate. The key move is applying De Morgan's theorem at the NOR gate. Finally, we'll verify everything with a truth table. Let's start. Notice the 2 gates on inputs A and B. Both are NAND gates with their inputs tied together. When you tie both inputs of a NAND gate to the same signal, it simply inverts it. So gate 1 gives us not A, and gate 2 gives us not B. Now here's the key step. These inverted signals, not A and not B, feed into a NOR gate. We need De Morgan's theorem here. NOR of not A and not B means we take the complement of their sum. By De Morgan's law, that simplifies beautifully to A and B. The double negation on each variable cancels out perfectly. But we're not done yet. That AND result passes through one more NAND gate, again used as an inverter. So the final output is not of A and B, which is exactly what a NAND gate does. Let's verify with a truth table. The output is 1 for every input combination except when both A and B are 1, where it gives 0. That's the NAND truth table, confirmed. The answer is option 2, NAND gate. 2 strings joined end to end, tied between 2 walls. A pulse shoots from each side. Which one takes longer to reach the joint? Here's our approach. First, we'll write the wave speed formula. V equals the square root of t over mu. Then we'll express each travel time as distance divided by speed. The key move is forming the ratio. Because the tension is the same for both strings, so it cancels out completely. What's left is just lengths and square roots of densities. Finally, we plug in numbers and simplify. The wave speed in a string depends on 2 things: tension, which speeds the wave up, and linear density, which slows it down. String A has lower density, so waves move faster through it. String B is denser, so its pulse moves slower. For string A, the wave speed comes out to 500 times the square root of 10 meters per second, about 1581 meters per second. For string B, we get 500 times the square root of 5, roughly 1118 meters per second. String B is slower, as expected, because it's heavier per unit length. Now, for travel times. Pulse from C covers 2.5 meters through string A. That's T1. Pulse from D covers 1.5 meters through string B. That's T2. Notice that when we write each time as L times the square root of mu over the square root of T, the square root of T appears in both. When we form the ratio T1 over T2, that root T cancels exactly, because both strings share the same tension. What remains is LA times root mu A over LB times root mu B. Plugging in, 2.5 times root 2 over 1.5 times 2. This gives us 2.5 root 2 over 3. Simplifying the fraction, that's 5 root 2 over 6, approximately 1.18. The pulse through string A takes about 18% longer, even though it moves faster, because it has to travel a greater distance. Water flows through a tube that narrows in the middle. The two vertical columns differ in height by 5 centimeters. We need to find the rate of flow. Here's our approach. We'll use the continuity equation to relate the speeds at A and B. Because the area at B is half of A, the speed must double. Then we'll connect the manometer height to a pressure difference using Bernoulli's theorem. Finally, combining both gives us the velocity at A, and from there, the flow rate. Step 1. Continuity. In steady flow, the same volume passes every cross-section every second. So, area times velocity is constant. Since section B is half the area of A, the velocity at B must be exactly twice the velocity at A. Step 2. Bernoulli's theorem. For a horizontal tube, faster flow means lower pressure. That's exactly what the shorter manometer column at B is telling us. The 5 centimeter height difference translates to a pressure difference of rho times G times 5 centimeters. Notice the density appears on both sides. It cancels cleanly. Step 3. Solve for the velocity. Setting the manometer pressure equal to the Bernoulli pressure difference and substituting the velocity ratio, we get VA squared equals 1/3. So the velocity at A is 1 over root 3 meters per second. Now the flow rate. Multiply the area at A, 6 square centimeters, by the velocity, converted to centimeters per second. 6 times 100 over root 3 gives 600 over root 3, which simplifies to 200 root 3. Here's a question that trips up most students. We've got a tiny charge sitting quietly at the origin, and we need to move another charge between 2 points in 3-dimensional space. Here's our approach. First, we'll find the distance from the source charge to each of the 2 points, using the 3-dimensional Pythagorean theorem. Then, we'll compute the electric potential at each point. The key move is the work formula, charge times change in potential. Finally, we'll verify the sign makes physical sense. Let's start with the distances. Point A is at coordinates 4, 4, 2, and when we square and add these, we get 16 plus 16 plus 4, which is 36, so the distance is 6 meters. For point B at 2, 2, 1, the sum is 4 plus 4 plus 1, which is 9. Distance is 3 meters. Notice how the exam chose perfect squares. This is always the hint. Now the electric potentials. The potential due to a point charge is K times Q over R. Our constant K times Q gives us 9 times 10 to the 9 times 10 to the minus 8. That's 90. So at point A, we get 90 over 6, which is 15 volts. At point B, 90 over 3 gives us 30 volts. Point B has double the potential because it's half the distance. Here's the key insight. Work done equals charge times the rise in potential. From A to B, that's 2 microcoulombs times the difference of 30 minus 15, which is 15 volts. Multiply through and we get 30 times 10 to the minus 6 joules, 30 microjoules. Option 2. And notice what we never did. We never calculated the path between A and B. Because electric fields are conservative, only the start and end potentials matter. That single insight saves enormous calculation time in any electrostatics problem. You can see the electric field oscillating. But where exactly is the magnetic field hiding? Here's our approach. First, we'll read the phase pattern, kx minus omega t, to confirm the wave travels in the plus x direction. And we'll compare the amplitude of the magnetic field to that of the electric field. That ratio is 1 over c. Finally, we'll confirm the amplitude ratio by plugging in the speed of light. That's the key to understanding the magnetic field. Then, we'll use the right-hand rule. E cross B equals the propagation direction, which tells us which axis B lives on. Finally, we divide E naught by C to get the amplitude. The electric field has a y subscript, so E points along the y-axis. The term kx minus omega t means the wave moves in the plus x direction. Now, for the pointing vector to point in x hat, We need E cross B to equal X hat. Since Y hat cross Z hat equals X hat, B must oscillate on the Z-axis, not the Y-axis. For the magnitude, we use B naught equals E naught over C. E naught is 69 volts per meter, and C is 3 times 10 to the 8. Dividing gives us 2.3 times 10 to the minus 7 Tesla. That's about 300 million times smaller than the electric amplitude. The phase is unchanged. In a free electromagnetic wave, E and B are always in phase. So we keep the same argument, kx minus omega t. The complete expression is Bz equals 2.3 times 10 to the minus 7 sine of that same phase. Option 4. Key insight. In any EM wave, E and B are perpendicular to each other and to the propagation direction. And B naught always equals E naught over C. You slide a dielectric slab into a capacitor, but only 1/3 of the gap. Does the capacitance just go up by K? Not quite. Here's our approach. We start by expressing the original capacitance in a useful form. Then, we recognize that the partial slab creates two capacitors stacked in series, one with the dielectric, one with the remaining air gap. Finally, we combine them using the series formula and simplify. The original capacitor has capacitance C in vacuum. The key move here is to write epsilon naught times A as C times D. This substitution lets us replace all the material constants with the single symbol C at the end. Now here's the crucial insight. The slab fills the full plate area but only 1/3 of the gap height. So the electric field passes through the dielectric first, then through the remaining air gap. That's a series connection. The same charge sits on both sections. Let's find each piece. The dielectric section has thickness d over 3 and constant K. So, its capacitance is 3 kc. The air section has thickness 2/3 d, giving capacitance 3c over 2. Notice how both simplify cleanly once we use our substitution. No messy constants left over. We now apply the series formula. 1 over c nu equals 1 over c1 plus 1 over c2. That's 1 over 3 kc plus 2 over 3c. Bringing them to a common denominator gives 1 plus 2k over 3 kc. Flipping it, c nu equals 3 kc over 2k plus 1. That's option 1. Quick sanity check. When k equals 1, we get back c. When k is huge, we approach 3c over 2, which is just the air gap alone. The answer is option 1. Here's a twist on Bernoulli's equation. Two mystery constants, A and B, have been built into it. Your job? Find their dimensions, using only the equation structure. Here's our approach. We use one rule. Every additive term must share the same dimensions as pressure. First, we'll isolate B from the gravity term. Then we'll use B to crack A from the pressure term. All three groups must have the same dimensions as pressure, mass per length per time squared. Look at the gravity term, rho times g times the quantity h plus bt. Since h is a height, bt must also be a length. So b times time equals length. That gives b the dimensions of velocity, length per time. Now for A, the modified pressure term, A over B times T squared, must also equal pressure. Rearranging, A equals pressure times B times T squared. We substitute B as length per time and T squared as time squared. Multiplying through the exponents, mass times L to the 0 times T to the minus 1. So A has the dimensions of mass per time. Matching against the options, A is mL0 T minus 1, and B is m0L T minus 1. That's option 4. The key insight, additive terms are your anchors. Match them dimension by dimension. Two different metals, joined as one rod. When heat is applied, what happens? Here's our approach. We have aluminium and steel rods of equal lengths joined end to end, 60 centimeters each, for a total of 120. First, we'll find how much temperature changes. Then we'll apply the linear expansion formula to each rod separately. We add both expansions to get the new total length. Since both rods have the same length, each is 60 centimeters. The temperature rises from 30 to 100 degrees Celsius. That's a change of 70 degrees. Notice how aluminium's expansion coefficient is exactly twice that of steel. The linear expansion formula says the change in length equals the original length times the coefficient times the temperature change. For aluminium, this gives us about 0.10 centimeters of growth. Steel expands half as much, 0.05 centimeters. Here's the key move. We just add both expansions together. 0.10 plus 0.05 gives us 0.15 centimeters total. Add that to the original 120, and we get 120.15 centimeters. The answer is option 3, 120.15 centimeters. The key insight? Equal length rods in series. Just sum their alpha values and expand once. A satellite is orbiting Earth quietly. You want to push it to a higher orbit. How much energy does that actually cost? Here's our approach. First, we recall that the total mechanical energy of a satellite in circular orbit is negative gmm over 2r. Then, we express gm using surface gravity, g times re squared. We plug in numbers for both orbits. Take the difference, and that gives us alpha. The total energy formula is the key tool here. In a circular orbit, the kinetic energy is positive gmm over 2r, and the gravitational potential energy is negative gmm over r. They combine to give negative gmm over 2r. The negative sign means the satellite is bound, and a higher orbit is less negative, so it needs more energy. We don't know big G and big M separately, but surface gravity gives us the product. Since G equals gm over re squared, we get gm equals g times re squared. With g equal to 10 and re equal to 6 times 10 to the 6, gm comes out to 3.6 times 10 to the 14. At the initial orbit of 1.5 Earth radii, R1 is 9 million meters. Plugging into the formula, E1 equals negative 2 times 10 to the 9 joules. At the final orbit of 3 Earth radii, that's 18 million meters, E2 is negative 10 to the 9 joules. The energy we need to supply is E2 minus E1. That's negative 10 to the 9 joules minus negative 2 times 10 to the 9 joules, which is positive 8 times 10 to the 9 joules.
Minus negative 2 times 10 to the 9, which equals exactly 10 to the 9 joules, or 1,000 times 10 to the 6. So alpha equals 1,000. Option 4. The key insight. A higher orbit always has higher total energy, so you must always add energy to climb. Never lose energy moving outward.
A 4-kilogram mass is pushed by a force that keeps growing with time, stronger and stronger in both directions. We need its velocity and position at 2 seconds. Here's our approach. First, we identify the force as a function of time. Then, we integrate that force to find the velocity. Finally, we integrate the velocity to find the position. That integration will give us the velocity and position we need. We divide the force by the mass, using Newton's second law to get acceleration, separately for the x and y directions. Then we integrate the acceleration to get velocity, starting from rest. Finally, we integrate velocity to get position, since the mass starts at the origin. 2 integrations, 2 components, and we'll have the complete answer. Divide each component of the force by 4 kilograms. The x acceleration becomes t cubed, and the y acceleration becomes negative 3t over 4. Notice these 2 components are completely independent of each other. Step 2. Integrate for velocity. The x component integrates from t cubed to t to the 4th over 4. The y component integrates to negative 3t squared over 8. Since the mass starts from rest, both constants of integration are 0. Now plug in t equals 2 seconds. The x velocity is 2 to the 4th power divided by 4. That's 16 over 4, which is 4 meters per second. The y velocity is negative 3 times 4 over 8. That gives negative 3 halves. For position, we integrate velocity one more time. The x position integrates to t to the 5th over 20. At t equals 2, that's 32 over 20, which simplifies to 8 over 5 meters. The y position integrates to negative t cubed over 8. At t equals 2, that's negative 8 over 8, which is negative 1 meter. The answer is option 4. Velocity is 4 I hat minus 3 halves j hat, and position is 8/5 I hat minus j hat. Watch out. Option 1 has the right velocity, but the wrong position. An alpha particle is fired at a gold nucleus, racing forward at incredible speed. But it never actually hits. Why? Here's our approach. First, we'll identify the key physical principle at the point of closest approach. The alpha particle momentarily stops, meaning all its kinetic energy has converted to electrostatic potential energy. Then, we'll set up Coulomb's formula for that potential energy, convert units carefully, and solve for the distance directly. Both the alpha particle and gold nucleus carry positive charges, so they repel each other like magnets flipped the wrong way. As the alpha gets closer, this repulsion slows it down. At the closest point, velocity hits 0. That's our key equation. Kinetic energy equals Coulomb potential energy. The alpha particle has charge 2e. It's a helium nucleus with 2 protons. Gold has atomic number 79, so its nucleus carries charge 79e. The Coulomb potential energy formula gives us U equals K times both charges divided by the distance d. Here's the trap most students miss. The energy is given in mega electron volts, but our formula needs joules. 7.7 MeV converts to about 12.3 times 10 to the minus 13 joules. Get this wrong, and the entire answer shifts by a factor of 1,000,000. Now we set kinetic energy equal to Coulomb PE and solve for D. Plugging in, K equals 9 times 10 to the 9, charges 2e and 79e, and our converted energy, the numerator works out to about 2,275 times 10 to the minus 10. Divide by 7.7 times 10 to the 6. The result is 2.95 times 10 to the minus 14 meters. That's about 30 femtometers, roughly 4 times the gold nuclear radius. The alpha gets close, but the electric field pushes it back before contact. So remember, closest approach equals K times Z1 times Z2 times E squared divided by kinetic energy. Always convert MeV to joules first. Answer, option 1. Covering just one slit in Young's double slit experiment shifts the entire fringe pattern. Here's why that matters. Here's our approach. First, we'll see how the transparent sheet adds extra optical path length to one slit, because it slows down light. Then we'll use the fringe shift formula to connect that extra path to the physical shift on screen. Finally, we'll plug in the numbers and solve for thickness T. When light passes through the sheet, it travels through a denser medium, which means it covers more optical path than if it had gone through air. The extra optical path added is n-1 times T. For n equal to 1.5, that's half of T. Now, the central fringe shifts to wherever the total optical path difference is 0. That gives us the shift formula. Fringe shift equals n-1 times T times D divided by D. This makes sense. A farther screen spreads fringes more, and closer slits amplify the shift. We need T, so we rearrange. T equals fringe shift times D divided by n-1 times D. Plugging in, shift of 0.2, D of 0.1, n-1 is 0.5, D is 50. The numerator is 0.02, the denominator is 25. So T equals 8 times 10 to the power negative 4 centimeters. Yet, it moves fringes by 2 millimeters. A metal rod is being pushed through a magnetic field. What force does it take to keep it moving steadily? Here's our approach. First, we'll find the induced EMF. because any conductor moving through a field generates a voltage. Then, we'll calculate the induced current using Ohm's law. Finally, we'll find the magnetic braking force and figure out how to keep it moving at a steady rate, which equals the applied force at constant speed. Step 1. The motional EMF. When rod AB moves rightward through the field, free charges experience a force that separates them, creating a voltage. The EMF equals B times L times V. That gives us 0.15 volts. Step 2. The induced current. Current equals EMF divided by resistance. That's 0.15 divided by 2, giving 75 milliamps. Now here's the key insight. The current-carrying rod inside the magnetic field experiences a braking force opposing its motion. That's Lenz's law. For constant speed, the applied force must exactly cancel this braking force. F equals B times I times L. Substituting gives 7.5 times 10 to the minus 3 newtons. That's option 1. The power you put in equals exactly the power dissipated in the resistor. A beautiful energy balance. A conducting loop sits in a sinusoidal magnetic field. How much heat does it generate in exactly one cycle? Here's our approach. First, we'll find the magnetic flux through the loop. Then we'll apply Faraday's law to get the induced EMF. Next, we calculate the instantaneous power dissipated in the resistor. The key move is time averaging that power, using the fact that cosine squared averages to 1/2 over a full cycle. Finally, we multiply by the period to get total energy. The loop is perpendicular to the field, so the flux equals B times area. That's sine of 100 T Webers. By Faraday's law, the induced EMF is the time derivative of flux. Taking that derivative, the EMF becomes negative 100 cosine of 100 T volts. So the peak EMF is 100 volts. The instantaneous power dissipated in the 100 ohm resistor is EMF squared over R. That gives us 100 cosine squared of 100 T watts. Notice how the power pulses between 0 and 100 watts as the field oscillates. Now we need the average. The time average of cosine squared over a full cycle is always 1/2. So average power equals 100 times 1/2. That's 50 watts. The angular frequency is 100, so the period is 2 pi over 100 seconds. Energy equals average power times period, 50 times 2 pi over 100, which gives us pi joules of energy per cycle, which simplifies cleanly to pi joules. The answer is option 3. Look at this potential energy graph. 4 different regions, and your job is to rank the force in each one. Here's the trap most students fall into. Here's our approach. First, we'll recall that force equals negative dV over dx, meaning force is the slope of the Vx graph, not its height. Then we'll read the slope of each segment, AB, BC, CD, and DE. Finally, we'll rank those slopes from highest to lowest to get the answer. The key formula is F equals negative dV over dx. This means the magnitude of force in any region is simply the steepness of that line segment. A flat line means zero force. A steep line means strong force. Now let's read the slopes. Segment BC rises steeply, from V equals 1 to V equals 4 in just 1 unit of x. That's a slope of 3, the largest. Segment AB rises from 0 to 1 over 1 unit. Slope is 1. Segment DE has a gentle drop, slope about 0.5 in magnitude. And segment CD is perfectly flat, slope 0, force 0. Comparing magnitudes, BC has slope 3, AB has slope 1, DE has 0.5, and CD has 0. Ranking from high to low: FBC, then FAB, then FDE, then FCD. That's option 4. The key insight: force equals the steepness of the Vx graph, not how high V is. Region CD has V at its maximum, and yet the force there is completely 0. A rod hangs from 2 strings. One string is cut. What happens to the tension in the other one? Here's our approach. First, we'll model the rod as rotating about end A. The remaining string makes it a pivot. Then we'll find the moment of inertia about that end. Next, we'll use the torque equation to get the angular acceleration. The key move is finding the center of mass acceleration from that. Finally, Newton's second law gives us the tension. Before the cut, each string holds half the weight. So each tension is mg/2. Most students guess that after cutting, the remaining string now holds the full weight mg. That's the trap. Now let's look at the rotation model. When string B is cut, end A is the only support. The string at A is inextensible, so end A can't move freely. The rod must rotate about it. At the instant of cutting, angular velocity is 0, so end A is momentarily the pivot. For a uniform rod rotating about one end, the moment of inertia is 1/3 ml². Gravity acts at the center of mass, which is L/2 from the pivot. The torque about A is just mg times L/2. And notice, the tension contributes 0 torque, since it acts right at A. Dividing torque by moment of inertia, the angular acceleration works out to 3g/2L. Since the center of mass sits at distance L/2 from the pivot, its tangential acceleration is 3g/4, downward. Not g, not g/2, 3/4 of g. Now apply Newton's second law vertically. Weight mg acts down, tension T acts up, and the net gives m times 3g/4. So tension equals mg minus 3mg/4, which is mg/4. Option 4 is correct. The key insight: because the rod rotates rather than falls freely, the center of mass only accelerates at 3/4 of g. The string only needs to supply the remaining quarter, mg/4. A charged particle falls right along the axis of a vertical solenoid. What is its acceleration? Most students expect the magnetic field to change things. Let's see exactly why it doesn't. Here's our approach. Identify all forces acting on the particle. Then analyze the direction of the magnetic field inside the solenoid. The key move is evaluating the cross product of velocity and field. Finally, Newton's second law gives us the answer. The particle has mass m and charge q released from rest. Gravity pulls it down with force mg. There's also a magnetic field from the solenoid. So could there be a magnetic force on this particle? Here's the key insight. A solenoid produces a magnetic field directed along its axis. Our particle moves along that same axis. So velocity and magnetic field are perfectly parallel, pointing in the same direction. The magnetic force equals Q times V cross B. When V and B are parallel, their cross product is 0, because sine of 0 degrees is 0. So the magnetic force is exactly 0 at every instant during the fall. Newton's second law gives ma equals mg. Mass cancels, and we get acceleration equals g. Option 3 is correct. The charged particle accelerates exactly like free fall. Can two simple lenses together magnify something 100 times? That's exactly what a compound microscope does. Here's our approach. First, we'll understand the two-stage magnification setup. The objective lens does the heavy lifting, and the eyepiece acts as a magnifier. Then we'll apply the normal adjustment condition, which tells us the eye is relaxed. Finally, we'll plug into the formula and read off the answer. A compound microscope multiplies magnification across two lenses. The objective creates a large real image of the tiny object, placing it at a distance L from the lens. The eyepiece then magnifies that image like a simple magnifying glass. Since we're in normal adjustment, the final image is at infinity. So the eye is completely relaxed. The objective magnification equals the tube length divided by the objective focal length. With L equal to 32 centimeters and focal length 2 centimeters, the objective magnifies by a factor of 16. This is why short focal lengths are used for the objective. Small focal length means large magnification. For the eyepiece in normal adjustment, the magnification is the near point D divided by the eyepiece focal length. D is 25 centimeters, FE is 4 centimeters, giving 6.25 times. Notice we use D over FE here, not 1 plus D over FE, because that formula is for near point adjustment, not normal. 16 times 6.25 gives exactly 100. The total magnification is 100. Remember this pattern: tube length over objective focal length times near point over eyepiece focal length. Two numbers, one multiplication, clean answer. Two rods, one pivot point, but the pivot's position changes everything, and most students fall for a classic trap here. Here's our approach. First, we'll identify exactly where point P sits relative to each rod. Then, we'll compute the moment of inertia for rod 1 directly using the end formula. After that, we apply the parallel axis theorem to rod 2, because its center of mass is far from P. Finally, we add both contributions and read off the answer. Looking at the figure, P is at the very top, acting as the pivot. Rod 1 is the vertical rod. P sits at its upper end. Rod 2 is the horizontal rod attached at the bottom of rod 1, so its center is a full length L away from P. For rod 1, since the axis passes through its end, we use the standard result. Moment of inertia equals m times L squared over 3. This is just 4/12 of m times L squared. No extra theorem needed. P is already at the rod's end point. For rod 2, we need the parallel axis theorem. The theorem says take the moment of inertia about the rod's own center. That's mL squared over 12. Then add m times the distance squared. The center of rod 2 is at the junction point, exactly L below P. So we add mL squared. That gives 13/12 of mL squared for rod 2. Now we add both. 4/12 plus 13/12 equals 17/12 of mL squared. The question tells us the answer is x over 12 times mL squared. Comparing directly, x equals 17. That's our final answer. Here's the key insight. Rod 2 is far from the pivot, so it dominates. Even though both rods are identical, rod 2 contributes more than 3 times as much as rod 1, purely because distance squared amplifies inertia dramatically. That's the power of the parallel axis theorem. A tiny beam of light, just 2 millimeters wide. Can two lenses expand it to 14 millimeters while keeping it perfectly parallel? Here's our approach. First, we'll recognize this as a Keplerian beam expander, a classic two-lens afocal system. Then, we'll compute the expansion ratio the beam needs to achieve. The key move is a single formula linking beam diameter to focal lengths. Finally, we'll plug in and solve directly. A collimated beam has all its rays perfectly parallel. When it hits a convex lens, those rays converge at the focal point. For the output to also be collimated, we need both lenses working together as a telescopic relay. Here's the geometry. We place the two lenses so their focal points coincide. In other words, the separation between them equals f1 plus f2. This forces rays to reconverge at the second lens's front focal point, which then recollimates them perfectly. Now for the key formula. By tracing a marginal ray through the shared focal point, we can show the output diameter equals the input diameter multiplied by f2 over f1. So the magnification of the beam equals the ratio of the focal lengths. Let's compute. The expansion ratio is 14 divided by 2. That's 7. So f2 over f1 must equal 7. With f1 equal to 40 millimeters, f2 is simply 7 times 40. That gives us 280 millimeters. We can verify. The lenses sit 320 millimeters apart. A ray entering at 1 millimeter height exits at 7 millimeters, exactly the 14 millimeter diameter we needed. The answer is 280 millimeters. This circuit has 5 resistors between A and B. But here's the thing. One of them carries 0 current. Here's our approach. First, we'll identify the Wheatstone bridge structure hidden in this network. Then we'll check the balance condition. If the bridge is balanced, that middle resistor is completely irrelevant. Next, we simplify to a basic parallel circuit, find the total current, and finally apply Joule's heating law. Look at the four arms. 1 ohm and 2 ohms on top, 2 ohms and 4 ohms on the bottom. For a balanced bridge, the ratio of resistances along each branch must be equal. 1/2 equals 2/4. Both give 1/2. The bridge is perfectly balanced, which means the connecting resistor carries absolutely no current. So we can ignore that middle resistor entirely. The top series branch is 1 plus 2, 3 ohms. The bottom branch is 2 plus 4, 6 ohms. Two parallel branches, 3 and 6 in parallel, give us an equivalent resistance of 2 ohms between A and B. Adding the 1 ohm internal resistance gives a total of 3 ohms. The battery drives 9 volts through 3 ohms, that's 3 amps. Power dissipated between A and B is I squared R. 9 times 2 equals 18 watts. In 1 minute, 60 seconds, the heat generated is 18 times 60, which is 1,080 joules. The key insight: always check bridge balance first. It turned a 5-resistor problem into a 2-minute calculation. The answer is 1,080 joules. Oxygen is sealed in a rigid container and heated from 30 to 40 degrees. We need to find the change in internal energy, and the question gives us Cp, not Cv. That's the setup. Here's our approach. First, we'll recognize this is a constant volume process, which means no work is done. Then we'll use Mayer's relation, Cp minus Cv equals R, to extract Cv from the given Cp. Finally, we'll apply the internal energy formula and calculate the answer. Constant volume means the gas can't expand, so work done is 0. From the first law, all the heat goes directly into internal energy. The formula we need is delta U equals N times Cv times delta T, and that's exactly what we'll compute. Step 2. We apply Mayer's relation. For any ideal gas, Cp minus Cv equals R. This works because at constant pressure, some heat goes into expansion work. That extra piece is exactly R per mole per degree. So Cv equals Cp minus R, which is 7 minus 2, giving us 5 calories per mole per degree. Step 3. The temperature change is simply 40 minus 30. That's 10 degrees. And notice that a 10 degrees Celsius change equals a 10 Kelvin change, so no conversion needed. Now we substitute. Delta U equals 10 moles times Cv of 5 times delta T of 10. That's 10 times 5 times 10, which gives us 500 calories. The answer is 500 cal. The key insight: internal energy always uses Cv, never Cp. Mayer's relation is the one-step bridge whenever Cp is given, but the process is at constant volume. Minus 48 to 70 seconds, about 55 words. Paragraph 5, Step 3, delta T, 71 to 83 seconds, about 30 words. Paragraph 6, calculation, 84 to 97 seconds, about 33 words. Paragraph 7, answer plus insight, 98 to 113, about 38 words. Total estimated, about 113 seconds.